Have you ever just stopped and wondered what is actually happening inside your computer? I mean, it really does feel like magic sometimes, right? Well, today we're going to pull back the curtain and demystify this incredible machine, breaking it down layer by layer to see how it all really works.
So, here's the big question. How does this box of metal, plastic, and silicon understand anything you do, from a simple mouse click all the way up to running some seriously complex code? That's the journey we're heading out on, from the physical parts you can actually hold to the invisible logic that makes it all possible.
All right, first things first. Let's start with the computer's anatomy, the physical parts you can see and touch. We're diving into the world of hardware.
To put it simply, hardware is all the physical stuff. It's the main computer box itself and all the things you plug into it: your keyboard, your mouse, your monitor. The rule of thumb is, if you can physically touch it, maybe even stub your toe on it, it's hardware.
Now, what's so cool is that no matter how complicated a computer seems, you can basically break down all its physical jobs into 5 key areas. These are handled by 5 major components that all have to work together as a team. So, let's meet the crew. First up, you've got the control unit and the arithmetic unit. Think of these two as the brain of the operation. The control unit is like the manager. It reads instructions and tells everyone else what to do. The arithmetic unit is the mathematician. It just crunches all the numbers. Put them together and you get the famous CPU, the central processing unit.
Next, we have the memory unit. You can think of this as the computer's desk or its workspace. It's the short-term memory where the CPU keeps all the programs and data it's actively working with, so we can get to them super fast. And finally, you have the input and output units. These are basically the computer's senses and its voice. Input devices, like your keyboard and mouse, are how you get information into the computer. And output devices, like your screen or a printer, are how the computer shares the results back with you.
So here's a quick look at how it all fits together. You've got the 5 key jobs. The CPU takes care of control and math, memory is for storage, and the input and output units let us talk to the machine. Honestly, this is the basic blueprint for pretty much every computer out there.
Now, speaking of memory, it's really important to know there are 2 different kinds. Main memory, like RAM, is that temporary workspace we talked about. It's incredibly fast, but it's forgetful. The second you turn the power off, everything in it vanishes. Secondary memory, like your hard disk or SSD, is the long-term filing cabinet. That's where you save your files so they stick around.
Okay, so we've got the body, the hardware. But a body needs a mind, right? Something to tell it what to do. And that brings us to the ghost in the machine, software.
The difference here is simple, but it's absolutely crucial. If hardware is the physical body, then software is the set of instructions, the programs, and the data that brings that body to life. You can touch the hardware, but you can't touch the software.
Software itself kind of breaks down into 2 main types. First, there's system software, and the big one there is your operating system, or OS. Think Windows or Mac OS. Its main job is just to manage all the hardware. Then, running on top of the OS, you have application software. These are the apps you actually use, like a web browser or a spreadsheet, to get specific things done.
All right, now we're going to the deepest level. How does software actually tell the hardware what to do? Well, it all comes down to a surprisingly simple language made up of just 2 numbers.
At its absolute core, a computer only understands logical operations. It thinks in binary. Every single decision, every calculation, every pixel on your screen gets boiled down to just 2 values. 1, which means true or on, and 0, which means false or off. That's it. That's the entire language.
So how can a physical machine process an abstract idea like true or false? It does it with billions of microscopic little electronic switches called logic gates. These are the actual physical circuits that perform those logical operations we were just talking about.
Let's meet some of the basic ones. First, you've got the AND gate. The AND gate is really strict. It will only output a 1, or true, if every single one of its inputs is also a 1. If even one input is a 0, the whole thing is a 0, no exceptions.
And we can see this perfectly in what's called a truth table. Just look at that output column. See that? The only time we get a 1 is in that very last row, where input A times input B are both 1. In every other case, the answer is 0.
Next up is the OR gate, and it's a lot more relaxed. The OR gate will output a 1, or true, if at least one of its inputs is a 1. It doesn't need all of them to be true. Just one is good enough.
And if you look at its truth table, the pattern is pretty obvious.
The only way an OR gate ever gives you a 0 is if both inputs are 0. Any other time, because at least one input is a 1, the output is also a 1.
And finally, there's the NOT circuit. This one is the easiest of all. Its only job is to flip the input. Whatever you give it, it gives you back the opposite. 1 becomes a 0, and a 0 becomes a 1. Its truth table is totally straightforward. Input is 0, output is 1. Input is 1, output is 0. It's always the opposite. And here's the truly amazing part. By combining just these three super simple gates, AND, OR, and NOT, in different ways, computers can perform every single complex task you can possibly imagine.
So, let's step back and tie this all together. We've seen the body, we've seen the mind, and we've seen the fundamental language. How do these three things work together to create the seamless experience we use every single day?
The huge takeaway here is that incredible complexity is built from layers of dead simple ideas. At the very bottom, you have billions of simple true or false logic gates. Software uses this basic binary language to write instructions, and those instructions command the physical hardware, the CPU, the memory, all of it, to do exactly what you want.
And that leaves us with a pretty mind-bending final thought. If everything, from streaming movies to composing music to developing artificial intelligence, can be built from nothing more than billions of simple on and off switches, what's the actual limit? What can't these machines eventually do?